This is worksheet number 7, and we're working again on conversions to symbolic language, and we're also going to do a couple proofs, even though it's not written here in class today. We did prove numbers 4 and 5, so I'm going to go through those proofs. And I did not include numbers 1 and 3, just because I didn't want to draw 3 truth tables, and I think that number 2... I don't know, it's debatable if number 2 or number 3 is harder, but number 2 just looked like a little trickier to me, so I decided to go with that one. Hopefully that's alright with you guys. And again, if you have questions about number 1 or 3, feel free to reach out to me or any of the other LAs. Definitely the written solutions will be posted, but if you do want a video solution or just something with a little more English explanation, feel free to reach out. So for number 2, prove that not P and Q and P and not Q or not P are logically equivalent. And this is like a lot to unpack and kind of hard to digest. I think the best way to go about this is to just start drawing a truth table. So we're just going to start here, P, Q, and we have true, true, false, false, and we could have true, true. It doesn't really matter what order you put these in. There might be a convention for it, but I think I'm going to be following convention inadvertently here. But it doesn't really matter as long as you get the 4 possible combinations. And now we want P and Q. And okay, so P and Q. So here it's true, and the rest it's going to be false, because for P and Q to be true, we need both of them to be true. False, false. And what else do we need? I guess we need not P and Q. And besides for these first 2 columns, the rest of the things that you need are going to be determined by your question. So here, in order to have not P and Q, we want to just start with P and Q. You don't have to do this. I just think that it's a little easier to follow. And it's easier to catch your mistakes if you do it this way. So I like to do more steps, especially when I'm teaching it to you guys. So not P and Q is just going to be the opposite of this column. So it's going to be false, true, true, true. This is quite tedious, which is why we didn't want to do 3 of them. Okay, so we need P and not Q. So let's do that. P and not Q. So this is going to be when P is true and Q is false. We need both these things to hold. We need P to hold, which means P is true, and we need not Q to hold, which means Q is false. So that's only going to be true in the second line. There. The rest will be false. And I'm actually going to take a bit of a shortcut here at the end. Now we just need or not P. We need this not P. And not P is just the opposite of P, so it's going to be false, false, true, true. Maybe I'll do timestamps on this video. I feel like that would make the experience better for you guys. Okay, so we have false, false, true, true. And now our last step is to do this whole statement. We're going to combine these 2. So we have P and not Q or not P. So P, oh, I made a mistake. Yeah, okay, I'm glad I caught this. I wrote or instead of and a few times over here, and none of you said anything. Let me just make sure. Okay. So yeah, all of these were meant to be ands. This eraser is terrible. Okay, I think that's what I want. Yeah, that's better. P and, not P and Q, P and not Q. Okay, so now we need not P and, what am I doing here? Oh, sorry. Okay, so here we have P and not Q. And not Q. That's a really ugly knot. Okay. Or not P. And that is going to be taking any row where one of these two columns is true. At least one of them is true. So in this top one, neither of them are true. So we're going to have a false. And the reason is because this is an or statement. So either this has to be true or this has to be true. And here, neither of them are. Here, the next three columns all have at least one true statement. They all have exactly one true statement. So therefore, those all get trues. And now our final question is prove that they're logically equivalent. And here's the proof. That is the same as that. False, true, true, true. That's the proof. Cool. Now, let's make this big. Watch this. Boom. Boomski. Okay. Hopefully I'll be able to draw on top of that. Good. Okay, now number 4. Write the following statement in symbolic language as a direct implication. Okay, so we need to do it with an arrow. That's what a direct implication looks like. It's got to be a statement with an arrow in it. Determine its contrapositive form. If y is an integer, then every integer of the form 4y plus 2 is even. Huh. If y is an integer. Okay, so that means that y is in the set of z. If that's true, that implies then it's an if-then statement. If this, then every integer of the form 4y plus 2 is even. So 4y plus 2 is even. That's it. If y is an integer, you could even ignore all of this. If y is an integer, 4y plus 2 is even. And I think the reason all those words are there are just to say that y could take on many different values. 4y plus 2 is even. It's in the set of e's. Okay, now we need to take the contrapositive. Contrapositive is not q implies not p. So if this part isn't true, that means that this part isn't true. Because the only way to get here is if we start here. The only way this is true is if this is true. Therefore, if this is not true, then this is not true. The mechanics are really simple, so I'm hoping that you get the concept, but even if you don't, the mechanics are very simple. We're going to flip this around and reverse it. So we're going to say 4y plus 2 is not even. Implies, it's the same statement, it's also an implication, that y is not an integer. Bam, straight through. Okay, this actually makes a lot of sense. So this first statement is saying that y is an integer, and therefore 4y plus 2 is even. But now we're saying, okay, well, 4y plus 2 is not even. So that means that y must not be an integer. Because if y were an integer, then 4y plus 2 would be even. The statements complement each other. They're actually saying the exact same thing, which is why a statement and its contrapositive are logically equivalent. So now let's prove this. And I think in class we proved the contrapositive. You could really prove either one. So let's go with the contrapositive, and we'll say, first let's say this in more positive terms. Instead of saying 4y plus 2 is not even, I want to say that 4y plus 2 is odd. And this will allow us to do some good stuff. 4y plus 2 is odd. And that implies that y is not an integer. It's not an integer. Okay, so I'm going to type a little because it's sort of a pain to do this. Let's make a big text box. And I'm going to write, for the sake of contradiction, we're going to do a proof by contradiction here. For the sake of contradiction, let's suppose, and let's remind ourselves how we do a proof by contradiction. In order to do a proof by contradiction, we have to assume that the premise, this first part, is true, but the conclusion is false. So in this case, we're assuming that 4y plus 2 is indeed odd. It is odd, just like our premise says. And remember, now our premise is the contrapositive, which is logically equivalent to the original statement. So we would be able to do a very similar proof if we use this statement. Our premise is that 4y plus 2 is odd, and that implies the opposite of what we're saying. Now we're going to contradict this part, that y is an integer. So for the sake of contradiction, let's suppose that 4y plus 2 is odd, and y is, capital is, an integer. I'm capitalizing to emphasize that this is the part that makes it a proof by contradiction. Okay, so that means that if 4y plus 2 is odd, we learned this, and I feel like I have to keep reminding you guys of this because it seems like in class we're not always remembering this. If 4y plus 2 is odd, that means that 4y plus 2 is equal, it could take the form of 2x plus 1 for some x in z. And I'm not writing the symbolic language here because I don't have it on my keyboard, but you would write it in the set of z, that x has to be some integer. And if you need a reminder for why this is a form that an odd number takes, think about the fact that all odd numbers could be expressed as a number plus the number below it, or the number plus a number above it. So let's say the number we choose is x, and the number above it is x plus 1. So if you add them together, you get 2x plus 1. And every odd number could be expressed this way. 5 is equal to 3 plus 2, 31 is equal to 15 plus 16, and so on. So every odd number could take this form. 4y plus 2 is equal, to 2x plus 1 for some x and z. And now let's do some algebra. So here we are assuming that y is an integer because that is part of our assumption here. And we're assuming that x is an integer because we just constructed it and we said that it has to be an integer. That's what makes this an odd number. So there's actually a really simple proof that you could do right now, and I'll show it to you. You could factor out a 2 from this side, and this will say 2 times 2y plus 1 is equal to 2x plus 1. We just factored out a 2 from this side. And now you can make the statement that we have even equals odd. this is a contradiction. There's multiple ways that you can finish this proof, but I think this is really elegant. So the fact that we were able to factor out a 2 from this means that this side is divisible by 2, and it's therefore an even number. This side is the form of an odd number. So we have some even number equals some odd number, which is impossible. That's a contradiction. So therefore, this statement is not true, which means that y must be an integer. Sorry, must not be an integer. So for 4y plus 2 to be odd, y must not be an integer, which is our contrapositive statement, which is what we were trying to prove. So that's one way of doing it. If you don't think you would have come up with the idea of factoring that out and done the even and odd thing, which I understand because I think that's not necessarily the most intuitive, you could also divide by 2 here and say that x, well, let's divide by 2, and we'll say 2y plus 1 is equal to x plus a half. And yeah, from this point, you could say that 2y plus 1 is an integer because y is an integer. It's one of our assumptions. And x is an integer, which means x plus a half is not an integer. And here we have an integer equals a non-integer, and we have a contradiction. So either of those proofs will work. Will get you the contradiction that we're looking for. And once we arrive at this contradiction, that means that one of our assumptions is wrong. Either 4y plus 2 is even, or y is not an integer. Those two things cannot hold at the same time. All right, hopefully that was clear. And now I will go to the last one after some erasing. And I haven't actually done the last one yet, so I'm going to be like figuring it out on the fly here. Hopefully it goes out okay. Write the following statement in symbolic language as a direct implication and determine its contrapositive form. Direct implication, again, means that we have an arrow. If y is an integer, okay, let's just write that. Y is an integer. And I think I see a lot of you guys are getting pretty natural at this. And x is an even integer. So we have a 2-part premise, and then we have our then. Our then is our indication, that's our arrow. Then means we're writing our implication arrow. So if y is an integer and x is an even integer, and if you say that x is even, you don't need to specify that it's an integer because integers are made up of the evens unioned with the odds. These make up all the integers. There's actually a symbol for that I think we learned. It's like that. I've never actually used this before, but this is when I don't know how to explain this actually. The evens and the odds make up all of the integers and they don't overlap. I think that's what this means. That was an aside, it's not so important. But basically when you say something's even, you're also implying that it's an integer because the evens are contained within the integers. That's what I was trying to express. So one person that I saw in class was trying to write that it's even and an integer. And while I don't think, I mean, you got the spirit right, but it's not necessary. Okay, so that's the first part of our statement. So y is an integer and x is even, and that implies then x times y is even. And this seems super, super intuitive. Like, you probably read this and was like, yeah, that's obvious. Whenever you multiply an even number by any other number, any other whole number, you're going to get an even answer. And yeah, that's true. And I actually want to do a direct proof for this one. We're not going to, maybe we'll prove the contrapositive. We'll see. I might just prove it directly. So now let's write the contrapositive form. So here we're taking this part and we're negating it. And then it implies the negation of this. And this negation is a little bit more tricky, but I think we'll be able to do it. So we're starting with this side. XY is not even. And I know it means that XY is odd. I just like to write it like this the first time because I think it's really clear what I'm doing. Whereas if I wrote that it's odd, you would have to understand that, I don't know, it just seems more complicated. It seems like 2 steps instead of 1. And in these instructional videos, it's really meant to clarify things and hopefully to not be confusing. So that's the goal here, is to make this as simple as possible. So here we're going to negate this statement. So that means we have to say y is not an integer. And how do we negate the and? We have to make it into or. So we're flipping the sign. Or x is not even. And we could think about this statement. So if xy is not even, we could also say that xy is odd. If xy is odd, that means that either y is not an integer or x is not even. It could be an odd number times an odd number, or it could be where we would just be negating this and y is still an integer. Because remember, only one of these two things have to hold. So it could be that we have an odd number times an odd number. Yeah, that would work. Okay, anyway, I don't want to get too into the weeds on this. So this is the contrapositive form. And now in terms of a proof, I'm actually, maybe in class or maybe on the worksheet, Professor Carbone is going to prove the contrapositive. I would prefer to prove this just because it looks fun. So maybe you'll get 2 proofs for the price of 1 here. So y is an integer and x is even. So I want to do a proof by cases here. And what tips me off to do that? I guess what tips me off is that I know that an even number times an even number is even, and I know that an even number times an odd number is even. And those are the 2 cases that this could be. We have to think in abstraction. It's really tempting to want to put a number on this, like say x is 8. And you're gonna get better at this. You're gonna get better at thinking in abstractions and thinking of integers as either even or odd. It just takes a little practice. But I think once I give that hint, hopefully you'll have an idea of how to complete that proof. And I'll walk through it now. So x is even, so that means that x takes the form of, let's say, 2e for some e that's an integer. That's what it means for a number to be even. It's 2 times an integer. And let's say case 1. We'll say that y is even. Case 2 will be that y is odd. So now we have 2e, and we'll say that y is 2 times f for some integer f. That means that xy equals 4 times e times f, which equals 2. In order to show that something is even, factor out a 2 and show that what's inside the parentheses is still an integer. That's all you got to do. 2 times 2ef. And that is even. And just to show this more explicitly, we factor out a 2 successfully, and then what's inside here is an integer because it's 2, which is an integer, times e, which we've defined as an integer, times f, which we've defined as an integer. Therefore, this is even, and our statement holds. Now we just have to look at the second case, and here we'll change up the variables. We'll say x is equal to 2j. Again, x is still even because x is going to be even no matter what. It's going to be the y that's changing. So here it's case 2. where y is odd. And this is actually, earlier when I was saying that z is made up of the evens and the odds, it's actually kind of important that the evens and odds cover all of the integers. Every integer is either even or odd, because if there were some integers that were neither, we would have a lot more cases to look at. Here we know that every integer is either even or odd, and therefore we only have two cases that y could be. Y could be even or odd and nothing else. So it actually does kind of come into play here. If there was some third thing that it could be, then we would have to show a third case where our statement still holds. So let's say that y is equal to, pick a letter. Let's do x this time. No, we can't do x. We're using x. Let's do z. 2z plus 1. And it's going to be the same drill, same process. So xy equals 2j times 2z plus 1, which is the same as, oh gosh, math. I did not do this on purpose. 4jz plus 2j. I'm not even a jz fan. Hopefully that doesn't offend anyone. And we could factor out a 2. We could have done this like in one step here, but you know, we're just doing things nice and easy, nice and slow. So we have 2 times 2jz. That's a z, I promise. Plus j. And that is even. Whew, we got through it, guys. It's even because we factor out a 2, and what's inside our parentheses here is an integer, because 2jz is an integer just like 2ef was an integer, because we've defined our j and our z. Oh, I forgot to define them, but imagine that I wrote j is an integer, and I did the same thing with z. I should have written that. And then we're adding j, which is an integer. So whenever we're multiplying and adding integers like this, and there's no fractions and there's no division, we could be comfortable saying that this is an integer. So yeah, that is the proof. And I know we have a test coming up, so I expect lots of questions. Best of